Hey everybody, thanks for coming. My name's Rijndael. I'm from Taproot Wizards, here to talk about inscriptions. Just kidding. We are here to talk about building covenants with OpCat, also known as BIP 420. That's the wrong link. It is BIP 420. So, actually, yeah, that's right. Eventually consistent systems are funny like that. So what I want to do today is, we've heard a lot today and probably in other discourse that you can use OpCat to build covenants. This is all based on some work that, what is up with the lights?
Sorry,
Yeah. Oh, okay, I gotcha. We'll just plow on. Yeah, that sounds great. Yeah, pay a higher fee. So this idea that you can build covenants using OpCat is based on some work that Andrew Polstra did in, I think, 2021. But a lot of people, even if they read that blog post, don't really understand what it is or how it works, mechanically how it works. That's led to a lot of people assuming that you can do things with OpCat-based covenants that maybe you can't, or that you can't do things that you can. So what I want to do today is to walk you through how you actually use OpCat with schnorr signatures to build covenants in Bitcoin. And the goal is not to go through like a full enumeration of everything that you can do. It's to give you some understanding of how this works mechanically, like what you would actually have to do in your program and in script in order to build a covenant this way, so you can get some intuition. Like, the goal here is that if you're thinking about a problem that you're trying to solve and you want to know if you could solve this problem with a cat-based covenant, I want you to have sort of a jumping off point to understand the kind of physics of this. And then we'll talk a little bit about some other opcodes that might be useful, and we'll look at some examples of how you can do this. So we're going to talk about two things. Mostly, we're going to talk about OpCat, and we're going to talk about schnorr signatures. This is the really short slide before we get into how schnorr signatures work. OpCat, super simple opcode. We take two elements on top of the stack, we concatenate them, and they go back on the stack. So you take A and B, cat them together, and you get AB as a single element. Schnorr signatures, and specifically schnorr signatures as specified in BIP 340, which is what we have in Taproot. We're going to walk through how schnorr signatures work. We're going to touch on how verification works, and then we're going to show how you can kind of abuse a schnorr signature to make a covenant. So a signature is a pair, R and S, and you can imagine having like a sign API or a sign method that takes in a message, a private key, and a nonce, which is like a one-time value that you never want to repeat. And it's going to return this pair of values, R, which is a point, and S, which is a scalar, just a number. And does everybody know what G is in SecP 256K1? G? Okay. So the way that we do key derivation for elliptic curves is there's this special point on the curve that we use in Bitcoin called G. It's the generator point. And the idea is that by adding G to itself over and over again, you can generate all the valid elements of this group. And so the way that we turn a private key into a public key is we multiply your private key times this generator point, and that gets you a public key. We do the exact same thing for your nonce, and that gets you this R value, which is the public nonce commitment. And then what we do is we construct what's called a tagged hash. So we want to make sure that if you construct a signature in kind of one context, that can't be replayed in a different one. So we put this tag, this little bit of context, inside of hashes when we're doing things in Taproot. And so you take your public nonce commitment, which is sort of like the pub key version of a nonce. You take the public nonce commitment R, the public key, and the message that you're signing over, make a tagged hash out of that, multiply it by the private key, and then add the nonce. And then these two values, your public nonce commitment R and this tagged hash that you've created S, these are S times D plus K, these two things are your actual signatures. When you look on chain and you see a 64-byte schnorr signature, like, this is actually what it is. And then I'll just go through this really, really quickly. It's a lot of math on the screen, but I just want you to be convinced that it works. The way that signature verification works for schnorr signatures is you basically reconstruct that tagged hash. That's this E value on the second line. And then we're going to check that R equals S times G minus E times P. And what you're basically doing is you're reconstructing this challenge, and then you're multiplying it by public information that you have, and if it matches the R value that's committed in the signature, then it's a valid transaction, or it's a valid signature. So we're going to dig into what's actually in this signature that lets us build covenants. So again, the second component of a signature, this S value, contains the public nonce commitment, a pub key, and this message. And I've just been saying message over and over again, not saying what it is. This is like the thing that you want to sign. So in BIP 341, which is like script and signature validation rules for Taproot, we have a common signature message. So whenever you sign over a Taproot Bitcoin transaction, there's a standard set of fields that get concatenated and hashed together in order to construct this message. So, and all of those things put together are at most 206 bytes. So this is my horrible drawing of a Bitcoin transaction. These are the normal components that you think about when you think about like what things are committed to in a transaction ID. So you've got your inputs, which are like a prev out. You have a transaction ID and a index. And then you've got your outputs, which are an amount and a script pub key. And you've got a version and a lock time. We also commit to some other additional information in this common signature message. We get the index of the input that we're spending from. We get amount, script pub key, and sequence numbers for all of our inputs. And then that saxophone in the bottom is meant to represent the annex. Nobody knows what the annex is, so it's a saxophone. So if you go and read BIP 341, this is actually all the fields that get committed to in this common signature message. I'm not going to read all of them, but some things to draw your attention to are that we have a lot of information about our inputs. So we don't just have the prev out, we don't just have the prior transaction ID and index, we actually have amounts, we have script pub keys, we have sequence numbers, we have some extra information if we're doing like an anyone can pay. So there's actually a lot of information in here that gets committed to when you sign a Taproot transaction. So that is what goes into this, this message here. And the hack, the thing that lets us do covenants here, is if you take this S value, which is this tagged hash, and you set D, which again is the private key, to 1, and you set the nonce to 1, then the R value, which is your public nonce commitment, this is K times G, is just going to be G. It's this generator point. It's a well-known thing. It's part of the definition of the group that we're working over. And then if you set your private key to 1, then the public key is G. So we end up with the S value for our signature is just this tagged hash of G concatenated with the message, which again commits to all the information in our transaction, times 1 plus 1. You can get rid of the times 1. And what you end up with is you can construct this schnorr signature that just is basically your message hash with some copies of G plus 1. And this is a valid schnorr signature for the private key 1 and the nonce 1. So what you can do with this is if you can actually build this signature on the stack or get this signature on the stack somehow and then call checksig, then if that checksig succeeds, then it means that the message inside of that signature matches what's actually in the transaction. So the values that you committed to in that message field must match the values of this transaction that we're inside of, otherwise checksig would fail. So this is how we actually do covenants with cat. So we're going to walk through what that actually means in practice. How do you actually use this? So what we do if we want to make a covenant is and the value here is that we get introspection. Johan was just talking about it's great if you can get introspection. If you want to be able to work with components of your transaction in your Bitcoin script, so you want to be able to introspect a input amount or an output value or an output script pub key, what you're going to do is you're going to take the elements that you want to be fixed. So you want to send to a specific script pub key, and you're going to either embed those in your script or somehow copy them into your script. And then all the free values that can vary depending on spend time constraints, you pass as witness data. And you use all of that to construct a BIP 341 signature message on the stack. So again, here's a subset of all these elements. You take them, commit to the ones that you want to commit to, and then the rest of them you pass as witness data. And if there's some tricks here where if we don't actually care about specific values, like maybe you don't actually need to introspect any of the inputs, you just need them to be there for the message to be valid, you can actually just pass the commitments and save on some cats and some hashing. And then you take each of these components, you cat them all together, and then you hash them to get a commitment. You cat all of the commitments together, and now you have a BIP 341 common signature message. So as an example, here's a bunch of these fields that need to be signed over in order to be a valid Taproot schnorr signature. You take all of these, you call cat over and over and over again. You get this thing, which is just all of them catted together, and then you hash it, and you get a signature message. Build a signature around that, and you're good to go. So we construct this signature message on the stack. We prepend it with some copies of G for our public nonce commitment and our pub key. We add on that tag for the hash. We saw that there was like a BIP 340 challenge tag. And then we hash the whole thing, add another copy of G, and we have almost a valid schnorr signature. Because if you remember, we don't end up with just this hash value. We actually need hash value +1. Thank you, 31-bit unsigned arithmetic. We don't actually have U256 arithmetic in Bitcoin script yet. Script restoration coming soon. So what we do instead is outside of the script in our application, we grind fields until the signature ends in a 0. So you got to pick a field in your transaction that you can just grind through. I've found that nlock time and sequence numbers work really, really well. On average, you do at less than 256 times. And then you lop off the last byte of the signature, and that's what you stick in witness data. So you have the first 63 bytes of a signature, put that in a witness, and then in your script, you add on a 0 byte, use equal verify to check that it matches the thing that you computed, and then you add a 0-1 onto the end of it and use that to actually do the check sig. So this first one is used to validate that you computed everything the way you wanted to, and then the second one is actually enforcing the covenant. So that's a lot. Sounds like a lot of steps. Tried to unpack it and make sure that it kind of stood on its own if you read the slides later. But the overview of this technique is you take the values that you want to enforce in your script. So this might be input amounts, it might be input sequence numbers, script pub keys, whatever. You fix those in your script. And then at spend time, and this is something that your wallet would do or your application software would do, you build up your transaction in memory, you grab all of those other values that aren't committed to in your script, and you pass them in as witness data, and then on your script, you cat and SHA all of them together to get this S value, and then you do check sig, and if it holds, then your fixed value is what's actually on chain, which is pretty great. So now we have covenants. We did it. We can all go home. So some things that we can cover are on the input side. We can cover prevouts. We can cover input script pub keys, which is surprisingly useful. We can cover input amounts, sequence numbers, and then you can tell which input you are. So you can say, this script must be in the first input, for example. And then on the output side, it's kind of normal output stuff. You get a script pub key and an amount. Some things that we could do with that, just as an example, are you could say all the data that I'm going to shove into the witness is going to be everything except for the destination. I'm going to fix that in my script. It's actually going to be committed to in a tap leaf. And I build up my signature. As I'm building up this common signature message, when I get to the output value, instead of pulling it from the witness stack, or pulling it from witness data, it's just already there in my script. So I build up the signature around this pre-committed value. And then if you validate the signature, then it means that coins are going to that destination. So this is a way that you can do kind of like an enforced output. If you want to say my coins can only go to this address or that address, you can actually enforce that with opcat. Some other little toy examples. In addition to fully specifying an output, kind of CTV style, where you specify both the destination address and the amount, you can actually mix and match. You could say for the first output, I want to go to a specific address, but any amount. And then the second output, I want to be a dust value, but it can go to any address. And you can mix and match these things depending on your application. Another example that you could do is you can take the output destination address, the script pub key, make a copy of it, and then use that copy when you build up the commitment on your inputs. And this is actually a way that you can enforce that the coins are being spent from an address back to the same address. So you can actually have covenants where the coins have to be spent back to the same address over and over again until there's some state transition and they can escape. And we'll look at an example of that now. So if you wanted to build a vault, I think vaults are kind of the stereotypical covenant use case because they're actually useful and you can generalize them in fun ways. What you want to have is you want to have a construction where you send coins into a vault, and then the only valid spend from that vault is to trigger a withdrawal. And when you trigger the withdrawal, you want to specify where the coins are ultimately going, and you want that specification to be binding. You don't want somebody to be able to change their mind later. And then after some time lock, the coins can be spent to their final destination, or at any time before they're completed, they can be swept back to the vault. So this is kind of the state machine that you get. And this gives you what people call reactive security, where you say, I've got my coins in the vault. When I want to withdraw them, I trigger that withdrawal. If I don't go and hit the big red button in 2 weeks, then my coins move on to where I was withdrawing them to. But if it's not me withdrawing my coins, if it's somebody who stole my keys, then I push a button and I sweep my coins back to the vault. This is like a really nice kind of basic reactive security setup that we could do in a couple different ways, but we'll see what it looks like in CAT. And just to number these, I'm calling this kind of trigger transaction 1, and then the recovery sweep is 2, and then the completion is number 3. So tricky thing, we don't have the ability to do a tap, tweak, verify in Bitcoin script. So you can't tell right now that a script pub key commits to a particular tap tree. So the way that you need to implement multi-step state machines using opcat is by having each of the different state transitions that can happen be different tap leaves, and then having the contract send coins back to itself, but using different tap scripts depending on when they are. So in our construction, we have this like contract address for your vault, and there's a trigger script that sends things back to the contract address. There's a cancel script that sends things back to the contract address, and there's a completion script that sends things to the target that you committed to when you did the trigger. So trigger is pretty easy. What we want to do is assert that the script's input is the first input, that like you're in the right spot. You're going to assert that the amount paid in on the first input matches the amount paid out on the first output. So if you have a 1 Bitcoin UTXO, you are spending one Bitcoin towards the trigger. We're going to assert that the first input script pub key matches the first output script pub key. So we're asserting that you're sending back to yourself. And then we're letting the second output be any script pub key. And this is actually how we designate the target. So we're saying, this second output is where I want my coins to go. And if you kind of imagine this as being the transaction graph, this transaction on the left is this trigger where we're sending coins kind of towards the withdrawal. And the second output, we're kind of just using to hold a little commitment to an address that we're going to use later. And if you take a Bitcoin transaction and you take the version field, serialized inputs, serialized outputs, and the lock time, and you hash all of them together twice, you'll get a transaction ID. And one of the fields that gets committed to in the BIP 341 signature message is the input prev outs, which include a transaction ID. So what we can do is we can actually take all of the fields for this serialized transaction and put them as witness data into our completion script validate that second output, and then hash it all together and assert that that transaction ID matches the transaction ID in our input prev out. So this gives us the ability not just to introspect our transaction, but we're now actually introspecting an output on the previous transaction. And this is actually a way that we can carry state forward in sort of a multi-transaction state machine, because you can have outputs that carry commitments or state roots or addresses or whatever they are, and then in a future transaction, you can validate that that output belonged to a transaction that fed the transaction that I'm in. So this is actually how we can do kind of cross-transaction introspection. So the way that works is we take all this previous transaction data in the witness, make a copy of that second output script pub key, the little picture there, and then we construct that TX ID and assert that the prev out TX ID matches. And now we have this script pub key that we know was spent in the previous transaction, and we can use that to assert that our output matches. So we can assert that we are sending coins to an address that we previously committed to. And then add a plain old CSV relative time lock, and we've got vaults. And then cancellation is really boring. You just make sure that the script input is the first one, and you make sure that the amounts match and that the script pub keys match. So this is our vault. Oop, there we go. So this is our vault, really basic state machine. You have coins, you start withdrawing them, and when you start withdrawing them, you commit to some amount of state. And then after a time lock, you're able to withdraw your coins that's contingent on that previously set state, but you have this cancellation path, and this cancellation path sends the coins back into the vault. And there's actually like a really interesting way that we can generalize this shape of a state machine beyond vaults. Because we can say, all right, what other things can we do where from a given state, we want to be able to go to specific outputs or specific shapes of transactions, and we want to let the next step, the next set of allowed state transitions to be contingent on the shape of a previous transaction. And we have the ability to carry a little bit of state with us, and we can dispatch to other state machines. We can do some really interesting stuff with this. One of them is, instead of this cancellation step just sending stuff immediately back to the vault, maybe this cancellation step actually sends you to another state machine that does a more complex conflict resolution. And in this conflict resolution step, if somebody wins, then you kind of go back to the trigger state and you're waiting on a time lock. And if somebody loses, then you just revault the coins. This is like a generalized version of a vault. And if you were in the room, I don't know, half an hour ago for Johan's talk, you heard him talking about Matt. If you didn't see that, you should go and watch the recording later. It was awesome. You should also check out Salvatore's talk, I think tomorrow, about Matt. Friday. And also check out the website, merkle.fun. Matt is a generalized challenge response protocol for doing optimistic verification of arbitrary off-chain computation. So you should watch Johan's talk. It's way better than my slides. But the idea is that you take some arbitrary program trace and you can take that trace, Merkleize it, and then add commitments for sort of the state of the system before and after each subtree. And then you can drive a interactive challenge response protocol between the challenger and the withdrawer, where they take turns opening Merkle commitments until they find the program step where they disagree, and then you actually execute that program step on chain. And you either get an equivocation and somebody wins, or you get a timeout and they get their coins back. So you can take this interactive challenge response game that lets you do optimistic verification of arbitrary off-chain computation and just sort of sub it in the cancellation path of our vault state machine. And now you have a method where you can say the coins in the vault are encumbered by arbitrary off-chain computation. Somebody can optimistically try to spend them, and then if somebody calls foul and issues a fraud proof, then you go through an interactive, multi-transaction process to actually resolve whether or not it was a valid fraud proof or if you're allowed to take the coins out. We thought this was a good idea. People write white papers. we thought that was boring, so we made an illustrated children's book. It's called Cat VM There and Back Again. You should read it. It's great. The protagonist is visited by the spirit of Satoshi and has to help people get off-chain where riches and adventure awaits. It's a lot of fun. I think you should read it. And we're trying to actually build this into a system that people can build real bridges and real contracting systems on top of. We call it Cat VM. It's kind of a cheeky name. It's basically MAT, but it only takes dependency on opcat. So it doesn't require additional covenant opcodes. The only thing that it needs beyond what we have today is opcat. So if we have opcat, we can build this optimistic withdrawal system where funds are handled by arbitrary off-chain computation. Anybody can initiate a withdrawal or a challenge if you have enough data to reconstruct all the trees. So it doesn't rely on having like a predefined set of people that you've done like pre-signed transactions over. All of these script commitments that you have to do can be computed kind of once per program and then just like kept in your client software. And you should definitely check out Salvatore's talk to learn more about it and Johan's talk. Some other upgrades that would be super, super nice for this, check contract verify or some other tweak add would be great. Check sig from stack. If I was Bitcoin king for a day, we'd have a ZKP verify, like no question, and we'd also do script restoration. It would be awesome. If you want to learn more about this, I think the best place to start is Andrew Poelstra's Cat and Schnorr tricks. There's 2 blog posts, read them. A lot of people have misunderstood them, so this talk probably made that worse, but maybe it made it a little bit better. There's also an implementation of all this. So we wrote a vault using opcat. It runs on regtest on your machine. It takes 3 commands to run, and you get a fully fleshed out vault that you can do withdrawals, you can steal, you can cancel, whole thing on regtest on your machine. It's called Perfect Vault. It's with cats. And then if you want to read the Cat VM book, it's at catvm.org. It is a great children's book that has a lot of good information about covenants and Merkle trees. If you read it to your children, I recommend a booming voice for the spirit of Satoshi. And that's it. Thank you so much. That was like half an hour. I'm happy to take questions over beers later. Oh, Lalu. Yep.
Test.
Oh, sure. I'm happy to.
Oh, should I go? Or?
Yep. It'll switch over in a second.
Okay, yeah, I don't know if I should wait or not. But given that you're constructing the sig hash, on the stack basically, and the sig hash, like you're saying, includes like, the like pre-input prefetch things like that as well, which scales the number of inputs. Like, do you do anything to get around like the stack limit? Because at a certain point, you only have the 520 byte, chunks basically, right?
Yep.
And I guess are you like how you're incrementally hashing that together, or
yeah. So like for each of the commitments that go into this message. So the max size of the final message when you're done is like 206 bytes because it's a bunch of commitments that are all catted together. So each of those commitments, like you have a single commitment for all of the input script hub keys. So you take all the input script hub keys, cat them together, and then hash it. So you have a single 32-byte hash, and that's like your input script hub key commitment.
Yeah.
Where you can run into trouble is if you have lots and lots of outputs or inputs, then you won't be able to build that commitment. I found in practice when I was doing the vault, when we've been doing some Cat VM stuff, we've been doing some also fun little like game things with Cat. In practice, like you don't end up with giant transactions for sort of like the middle of your state machine. You might have like a giant transaction like funding the initial contract, but if you're not trying to introspect those things sort of on the way in, then it's okay. Where you're more likely to run into the 520 byte limit is actually when you're doing this like state passing trick, you have to pass in the full like serialized transaction. So like all the inputs, all the outputs. And so if that's a big transaction, you can run into that limit. The limit that I ran into first was there's a relay policy limit on the maximum witness item size of like 80 bytes. So for this serialized transaction, you have to pass it in as pieces and then cat it together.
Gotcha. No, yeah, that makes a lot of sense because, like, pre-seg wit, you actually hash an entire transaction.
Yeah.
But then, in order to fix the quadratic,
Yeah, so you don't have to pass
goes a lot
witness data
better.
in, which is
Yeah.
great. Yeah,
Oh, cool.
you're just doing input and output serialization.
Cool. And then the other question I had is like, you're saying that you're going to basically pass like the free elements as like witness elements, right? But it feels like maybe that's a foot gun because otherwise, like that opens you up to basically malleability, right? So imagine if you had like a script that was like op if, check sig, and then else something else. Someone could potentially modify one of those free elements basically to have an invalid state, which would cause you to go to a different branch. I feel like that would be only bad like if you had unconditional branching basically versus acceptance or not. But that's just like one thing that popped into mind. And like, malleability is a concern here if you're passing things to the witness, but maybe in the future, if you had checkers from stack, you could have those be signed. And then at least that's some authentication, but maybe it doesn't solve all. But it's potential
right
foot
now
gun for architecture or for something like
Yeah,
this.
you can't do any like authentication over the elements. You're really just doing like assertion against like the structure of the transaction. It's like something that we're playing with. There's been some really interesting. There was a Delving Bitcoin post. Lalu and I were talking about this. So I'm saying this for the benefit of everyone, right? But so there's a really great Delving Bitcoin response where somebody took Alloy, which is like a model checker, and they like modeled out this construction, and they found like a bunch of issues, and like we've been talking about it. And so like these things are complicated. It's nice that you can do. That you can kind of mix and match which things you want to have commitments over, and you can do that with like a really low-level building block. But I do think what we're going to need if people want to use this stuff at scale is really good tooling for like authoring these contracts and for analyzing these contracts. I've been having a lot of conversations with people about building like a builder abstraction where you have a bunch of gadgets. So you say like, I have the input introspection gadget, I have the output introspection gadget, and you just say like, I've got a builder, I want to add these gadgets, and it builds up the script, and it also builds up the requirements for what witness data needs to be passed in. Because depending on which things you're introspecting, you might be able to save some bytes with like, you're going to be checking that an input address and an output address match, so you should like copy that instead of passing it twice. And there's some kind of like, if we know the pre and post conditions for like what things need to go on the witness, then we can glue them together the right way. But it's a lot of work.
Yeah, looking forward to playing with that tool more. Or I'm working on a little demo myself
Yeah,
too.
I don't want to say it's like a mini script, but it's it's something like that. It's a Bitcoin tooling joke. If you guys don't laugh, I'm going to start telling algebra jokes. What's purple and commutes? And a belly and grape. Okay. Yeah.
I think this is a dumb question, but I just want to ask you. So what events go into the trigger state again? Like, in other words, how do you...
Yeah, so I don't think I put it in the slides, but it's in the code, and you can go run the code. So the trigger state requires, I'm trying to remember how it works. It's based on the number of inputs and outputs, and it constrains the number of, it constrains one of them. I don't remember, but there's a way to do it. Yeah. Sorry. Yeah, I haven't looked at that code in a couple weeks, so I don't remember. But it works. Anybody else? Cool. Feel free later. Coffee, beer. Happy to talk about cats. Thanks.